Okay, so math review. Let's now talk about the math you're supposed to know for the case study and for this course. And your first written test is going to be mostly based on the math review lecture, just to make sure you're comfortable with all the basics. We're going to review propositional logic. We're going to review predicate logic, and also sets, relation, and functions. And hopefully we can do most of these too. At least this one, at least. Okay, we'll see how much we can do. We'll go slowly. All right, propositional logic. Okay. I'm curious, what if I stop propositional logic? Okay, a proposition is basically something can be either true or false, easy. That's why we got some truth table for you to understand, for you to remember. And we got logical operands for the proposition, which would be either true or false, right? You can manipulate the true and false in the proposition. And we use logical operators to build complex expression in proposition. And we got negation. We got, okay, so truth table, negation, trivial, right? I don't need to even go into detail. And also we got conjunction, disjunction, implication, equivalence, if and only if, right? We'll get to them. But let's now clarify something very important, which might be, I remember you guys mentioned before, for this course, okay? Whenever we talk about implication, let's use the following notation. Okay? Not the single. Okay, this is the convention for this course. This also corresponds to how you're supposed to type implication in Rodent. So it's good to stick to it. All right, implication. And accordingly, when we talk about if and only if, which I'll say a little bit more later in the lecture, also we use this rather than this. Not the way to go. Okay? Okay, let's go back. And conjunction, disjunction, everything, right? And I think a conjunction and disjunction are very, very easy, right? But I do want to discuss a little bit about, for example, conjunction symbol here versus ampersand in Java. And also the disjunction here versus vertical bar in Java, right? One is logical operator. The other one is programming operator. I want to discuss a little bit about the distinction in a moment. And I would also like to discuss the truth table for implication. I think that's maybe where usually confusion can come from. I want to talk about these two things. Let's talk about implication first. How about that? Okay, implication first. The way to think about implication is P implies Q, right? And we say P here is called the antecedents assumption or premise, and Q is a consequence, right? I'll just write it down here. And there will be some analogy I would like to show to you as well. So here we got P implies Q. Right? So here we say P here is the antecedents, and Q here is the consequence. Later on, when we get to the case study, we're going to use something called sequent calculus. We definitely need the implication as well to really understand the meaning for sequent calculus, but we'll get there. Let's talk about the analogy. The analogy would be, think about the antecedent is something you're promised. So P here is the promise terms. So we are talking about a contract. And the Q over here being the consequence. So these are the duties you're supposed to fulfill given the promise terms. For example, if you're promised on your employee contract, your hiring contract to say, you're paying, let's say, 100K per year, given that you will try to implement some software projects, right? And we want to use this analogy over here to understand what does it really mean for the truth table for implication. Now think about the implication being true is going to correspond to whether or not the contract is actually honored. If the contract is somehow honored, the result for the implication should be true. If it is not honored, then if that's breached, in that way, implication should be false. Okay, let's see. Let's start with the simplest one. Okay, if you're really getting what you were promised to be paid, that means you got true for the antecedent. You got a promised term. And accordingly, you also did your job. In that way, is the contract honored? Indeed, right? So that's why true implies true is going to give you true. That's the simplest case. Given that the promised term is really given to you, and also accordingly you did your duties, in that way, the contract should be honored. Okay, so that's why we see P implies true implies true is equivalent to true. That's why. Now, what can be a false case? Well, if you are given the promised terms, but you did not do your job, in that way, that should be false. That means the contract is breached. So if you got true over here, but you're given the money, but you didn't do the work, in that way, the contract is breached. That should be equivalent to false. So this is the only case where you're going to get a false for implication. Of course, formally, you will see that antecedents is true. So let me get rid of that. If the antecedent is true, but the consequence is false, you're going to get false. But the way to understand it would be, if you got something you promised and you didn't do your job, it's going to be false, right? Think about both ways. Are we okay for this? Okay. Now, there are the other two cases, right? What if, let's say, your promised term is not really given to you? Let's say you were promised to be given 100K in the contracts. Somehow your company said, no, unfortunately, we cannot give you that much, even though you signed the contract. Now, let's say you are so ethical, you still do your work. In that way, is the contract really honored? Yes, because, well, in some way, if the promised term is not even given to you, the contract doesn't matter what you do. It's already like a void. It's not breached, so that should be true. Let's say here, you were not given what you were promised, and you chose to quit. You chose not to do anything. Are you really breaching the contract? Not really, because the terms given to you was not even given, right? So that should be equivalent to true. So here, this case is saying the contract is not considered violated. All right, so that's just some informal analogy in case you forgot about what a truth table is supposed to be like for implication. But now let's get a little bit more formal here. I want you to look at some cases here. For example, here, when the antecedent is simply just false, right? In that way, it doesn't really matter what the consequence is, and the result for the implication will just be true, right? This is something called the zero of implication, all right? Which is, if I got false implies P, doesn't matter what P is, it's simply equivalent to true. And P can be any proposition, either true or false, right? That's maybe you have heard about that term before. The other two cases is like this. Given that the antecedent here is true, does the consequence matter? Yes, it does. If the consequence is T, the result is T. If the consequence is false, the result is false. So it really depends on that. So in some way, given that this is already true, the result here really depends on what the consequence is. And that's called the identity of implication. Okay? Identity of implication. So true implies P is equivalent to P. All right? Hopefully you have seen this before, and it's now good to recall. Right? So these are the important two theorems for, or axiom for implication. And if you forget about the truth table, you can always think about this counter analogy. So that's why I'm bringing that up. Okay? Any question about the truth table for implication? The reason that I really want to mention this is because for all these cases over here, we'll run into certain proof pattern that's going to depend on the result over here. So make sure you understand every case over here thoroughly. Okay? Okay? And then let me now talk a little bit more about different terminology over here. Okay? Yeah, so everything has been covered over here. Okay? And now we got different ways to refer to an implication, right? This slide can be a little bit tedious, but I think it's good to go over the different terminology. Okay? The first one. By the way, so let me just give you an overview. So we can say P implies Q. That's a formal term here, obvious. But when you hear people say the following, they really mean the same thing. If they say Q is P, that really means P implies Q. If they say P only if Q, they also refer to P implies Q. If they say P is sufficient for Q, they're also talking about P implies Q. If they say Q is necessary for P, they also talk about P implies Q. Finally, if they say Q unless not P, they're also talking about P implies Q. So we got how many? 1, 2, 3, 4, and 5. 5 different ways to really refer to P implies Q. That's my point. All right? And how do we understand each one of them? I think each one of them has certain good thing about they are really referring back to the truth table that we just developed a few minutes ago. Okay? Let's now take a look at some of them. And for some of them, you can definitely also try to look at the slides, and they are deriving a similar way. Let's take a look at a few of them. Okay, let's start with this. Let me start with, how about, to give you one example. So we are really talking about P implies Q, right? Just remember, that's what we are saying. That's what you normally understand. And what does it really mean when we say Q unless not P? Okay? This is saying the following. In order for this particular implication to be true, there are two possible ways. Either you say Q itself is true. That's condition number 1. Or you can say if Q is happen to be not true, you can also say not P is actually true. Either way. However, when both conditions are false, the implication will be false. And what this is really telling you refers very nicely back to the truth table. Let's take a look. Okay? Very closely connected to it. Let's see connection number 1. When we say Q here, if Q is true, Q is true, P implies Q is already true, right? Q is true, P implies Q is also true. So this Q here covers both cases here. What about not P? Not P means P is false. P is false, true. Overlapping, that's okay. P is false, also true. So we covered 3 cases already. What about the remaining row here? The remaining row over here tells me that neither Q nor not P is the case. In that case, I should really get P implies Q being false. So you can see Q is not true. In that case, I got Q being false. I got not P is, well, not P is not the case. That means P is the case, which means it is true, right? So you can think about here, when not Q and not the case, not P. P implies Q is false. Don't lose the big picture. What this saying over here is telling you, I'm basically saying this to correspond to all the 4 cases in the truth table. Either when Q is actually true, which will cover these 2 cases, or when the not P is the case, which will cover not P, which will cover this case, these 2 cases. The remaining case is if neither condition will be satisfied, in that case, the implication will just be false. That's what it is saying. Are we good for this? Okay, you really gotta maybe look at the slides and then try to think about what I'm saying here to see the correspondence to really appreciate what this single sentence over here is really telling you the truth table. Okay? Let me also do this one here and this one here. These 2 are basically the same thing. I can refer you to the slide. Let's just do 2 more very quickly. Okay? Let's say this. Q if P. What does that really mean? Okay? This really means given that P is true, given that the antecedents over here is already true, what would be the way for the whole implication to be true? Consequence is also true, right? The only way for P implies Q to be true is when Q is also true. That's really the main message over here. Let's see how that corresponds to the truth table. Let's take a look. When P is actually true, the only way for P implies Q to be true is for Q to be true. That's the first row. All right? When P is actually true, however, it turns out Q is not true as expected. In that way, implication should be false. Right? It's basically saying the same thing, but the opposite side. What about the remaining 2 rows? If P is simply not true, like a false, in that case, we don't care. We simply just treat the implication over here to be true. We simply don't care. So it's not false. Okay? So what we have seen so far is you really want to see from these 2 informal descriptions over here to see how they correspond to all the 4 cases in the truth table. That's the main message. Okay? Are you good? Yes, question, please. You may have to. You may have to. So I would say, for example, I might give you, let's say, for example, I might say, I'll put it down here. Example. I might say x larger than 0 if y less than or equal to 10. For example, that's what I put for you, right? In that way, this is in some ways still English, but I'd say translate this into proposition. How would you do it, right? In this way, you should really translate it into y less than or equal to 10 implies x larger than 0. That's one way, right? Maybe that's what you were asking? Or which part is not answered? Let me know.
unless, like...
Yes. Yes, it's possible. I might just give you some informal description using these languages, and then I say now formulate them into propositional term, in which case you have to identify which one should be the antecedent and which one should be the consequent. Yes, it's possible. Absolutely. Yeah. Okay, that's good. That's the example here. And then you can see the rest in a similar way. I want to do one more thing together with you, which is to understand if and only if, which is interesting. Now, this. When you actually got P if and only if Q, right? Now that you already, of course, after you study these terms, but now you're still learning, that's okay, I'll just tell you. The way to understand is like this. You can have either this way, right? Or you can have this way. All right? And I want you to convince yourself, right? It's either going this way or it's going this way, right? Now, this one over here is really the P only if Q. Okay, convince yourself when you study this, right? Might seem a little bit tricky, but you just want to refer to the definition. And this one here is the P if Q. Sorry? Yep. Question? Oh, I beg your pardon. I might say it wrong, right?
Yeah.
Thank you. I got the opposite. Beg your pardon. Thank you. Let me do it again. Thank you. So, what I meant to say is here. This one over here is really P only if Q. Agree? And then this one here is really P if Q. So the way to do it is P if and only if Q. Right? Maybe you have seen that already in the math class. You're going to be careful about which side is which. Right? This part versus this part. Okay? Yeah, terminology. Just make sure you understand that. And then I do have some discussion to be done about the conjunction, but I'll leave that maybe to Tuesday. I would like to go a little bit further, just about the syntax for universal and existential quantification very quickly. And then we'll continue on Tuesday. How about that? Yeah, we just got some more terms over here. Inverse, converse, and contrapositive, right? Just very quickly. So this might be something you have seen also before. Let's now remind yourself quickly. Oops. All right. Let's say if I have some implication here. P implies Q. Let's given this. If I want to get the inverse of this, I basically just add negation to both sides. Not P implies not Q. Easy. And what about converse? Basically switch the antecedent consequence. Rather than P implies Q, it would be Q implies P. All right? Now, there's another thing called contrapositive. Maybe you have heard of it before. Contrapositive. And it is another way to say that would be, it will be the inverse of the converse. Okay? The inverse of the converse. What does that mean? Inverse of converse. Why don't we do the converse first? Converse of this one here is Q implies P. And then if you want to take the inverse of that, simply say not and not. All right? And what is so important about contrapositive? I'm pretty sure you learned about this one theorem there to say P implies Q is equivalent to its contrapositive. Not Q implies not P. Right? For this course, you don't need to prove it, but you need to be aware of this. Okay? Good. And I also talked about the identity and zero of the implication earlier, right? So that one is also good. I would suggest I will use 10 minutes or less to talk about briefly the universal and existential quantification just on the paper. And then I'll go over some slides on Tuesday. Okay? That'll be the plan. And then we're fine. We're done. Here. So propositional logic is very easy. It's only about true and false. And you want to make sure you understand the truth table to begin with for implication. And over the weekend, try to spin your brain a little bit more about how each individual one is really corresponding to the truth table as I try to explain. Okay, that's your little homework in addition to lab 1. And also some theorems about implication. So what I want to do now briefly is to explain or to brush out your mind about universal and existential quantification. That's important. Okay, let's just understand the syntax a little bit. And then I'll show you some very interesting connection to some loops that you may have to write back in your maybe 1021 course from the first year. Okay, I'll draw the connection on Tuesday. Okay, of course, you got to understand this is for universal quantification. And this one here is for existential quantification, right? Let's get the term very well understood. Existential quantification. And the R over here is a predicate, which will specify a certain range. And this is what we call the universe of disclosure. You will see that on the slides. If you want to understand really the very important difference between propositional logic and predicate logic is you actually got some range of values to consider for the true and false. That's really the main extension from propositional logic to predicate logic, right? It's really the universe of disclosure. And for, I'll get to you. But for this course, usually when you specify this range, they should be finite. Should be finite, okay? But we'll see example next time. Question, please. Universe of disclosure, yes. Yes, exactly what I wrote over there. Okay. And the P over here are really the properties to be asserted. To be asserted. Okay, we understand what R is, we understand what P is. Okay? And for now, don't worry too much about the implication and conjunction here. Of course, you got to get it right. But let me just talk about the overall meaning first. What does the whole thing really mean? And what does the whole thing really mean? So you can just make sure you understand that part before you come on Tuesday's lecture. Okay? Let's now, first of all, talk about the universal first. If you consider this whole thing over here, okay, this whole thing. This is to say, for each I, if I satisfies R, then I satisfies P. And something for you to think about. Here. because this is an implication, what makes this true? When you study, once you study the truth table for implication, I want you to come back here in this context. In order for this universal quantification to be true, you have to make sure this implication holds, but under what circumstances? Think about it, and then we'll get you more insight on Tuesday. And what about this guy here? This one here is to say there is at least one I. There is at least one such I, such that I satisfies R and I satisfies P. And important to notice the difference here. One is about if, then. The other one is and. They correspond to these two. All right? A final question here, and I'll let you go earlier today. Question for you to think about. What happens if R of I corresponds to an empty range? That means empty universe of disclosure. An empty range. What will be the consequence to this one over here? And what will be the consequence to this, right? I'm going to tell you the answer on Tuesday, but before that, it will be very nice for you to figure this out to yourself. All right? Everything is good? Thank you so much. Have a good weekend. I'll see you next week. One moment.